Okay, usual blurb. Homework 3 is now on Sakai, due a week from Friday with the usual 1 week grace period. If you haven't turned in homework 2, please try to turn it in as soon as you can. And today and for the next week, we're going to be covering bootstrapping, and I guess I should put like my little Surgeon General's warning at the beginning of these next couple lectures. Bootstrapping, this is probably one of the very few introductory statistics classes in this country that covers bootstrapping. In fact, I, bootstrapping doesn't really even get covered in the advanced courses for our graduate students here at UNC and at a lot of universities, and a lot of my colleagues look at me like, you're doing bootstrapping in an intro course, are you nuts? It's I think a lot of the reason it doesn't get covered is just kind of inertia. That, to me, it's one of the most important advances in modern applied statistics and should be covered, but the textbooks just haven't caught up to that. And it's just incredibly powerful, as I'll discuss today. And I don't think it's that horrible, but it is more complicated than a lot of the stuff we've discussed thus far. So for the purpose of this class, I'm not going to ask you to do much more than just basically copy some examples that I work in lecture. But I'm telling you this not to try to scare you, but just because in the past, a lot of times after today's lecture, people are walking out, they're like, oh my gosh, I'm going to fail this class. Don't worry, you're not going to fail this class. This is mainly just so you're aware that this stuff exists, and the homework I will try to make as humane as possible. So, if I haven't scared you to death already, what the heck is bootstrapping and why do we care about it? Well, recall from a week or two back where we discussed sampling distributions, and once again I lost all my X bars when I went from OpenOffice to PowerPoint to Keynote, but this is supposed to say the distribution of the sample mean X bar is different from the distribution of the original data, and as we discussed in class a few weeks ago, if some mild conditions are satisfied, the sampling distribution X bar will have a normal distribution when n is sufficiently large. If you recall the Loblolly Pine data that's built into R that we used for a couple examples, that if you just take the raw data and plot a histogram, that is very clearly non-normal, just kind of mixed distribution of different tree heights. But when we took a bunch of samples of size 10 from this data set and took the mean of each sample of size 10 and then plotted the histogram of X bar in this case, see it's already looking approximately bell-shaped. So if we want to make inferences about the mean, we can use the fact the sampling distribution of the mean is normally distributed, that if we take the average of 30 things, then the average of these 30 things should have a normal distribution or a t-distribution as the case may be, and you can use that to perform hypothesis tests and calculate confidence intervals and stuff like that. Yeah, I guess basically said this, as we discussed before, the central limit theorem says you draw a sample of n independent observations from any population with mean mu and standard deviation sigma, then for sufficiently large n, the sample mean X bar will have a normal distribution with mean mu and standard deviation sigma over the square root of n. So, what's the point of bootstrapping then? Well, if you want to make inferences about the mean, we know the sampling distribution of the mean, so it's easy to calculate, for example, the 2.5 and 97.5% quantiles of the sampling distribution of the mean, and use that to give you a 95% confidence interval for the mean, for instance. Let's say we didn't know the sampling distribution of the mean X bar, and let's say there's no central limit theorem, or we didn't know the central limit theorem. We want to just try to estimate the sampling distribution on our own. So, is there any way to estimate this? Well, one thing that one might try is just sampling from your data with replacement. What does that mean? Why would we want to do it? Well, Recall, we briefly discussed this when we talked about sampling, but to sample with replacement, the prototypical balls and urns example, say you have an urn full of a bunch of balls, you reach into the urn, pull out a ball, and make a note of which ball you pulled it out, then put it back in and repeat the process and do this a certain number of times. The idea is, since the ball goes back in the urn after you draw it, you could draw the same ball more than once, or you could end up drawing certain balls not at all. For example, if you use the sample command in R, and if you want to tell R to sample with replacement, you can use the sample command with the parameter replace equals true. So the first example here, I sample from the numbers 1 to 10 with replacement. So you see, for example, I get 2 4s, I get 2 1s, I don't get any 3s. Then I repeat this a couple more times. Down at the bottom you see like I get 3 1s, 2 3s, and no 2s and no 7s, for instance. When you sample with replacement, some of the observations you're going to sample more than once, some you won't sample at all. And so you'll notice in this really simple case, say like we took the mean of the numbers 1 through 10 after sampling with replacement. Well, we won't get exactly the same mean every time. If we just take the mean of the numbers 1 through 10, it's obviously 5.5, but if we take the mean of this set of numbers there, this set of numbers there, it's going to be slightly different from 5.5. So, in general, just some notes on R. If you say sample x replace equals true, that'll sample from the vector x with replacement. And as I said, if you sample with replacement, it means that after you put an item in your sample, it gets returned to the proverbial pot, so there's a chance that you could select it more than once. When you use the sample command in R, if you don't give it the sample size, it's assumed to be the same length as your original vector. If you want a different sample size, then you could say sample x length n to get a sample size 2 or a size 10 or whatever. So let's say that we don't know the sampling distribution of the sample mean x bar. So we could try the following procedure to estimate it. And the Loeb-Wally Pine data has 84 observations, if I remember right. So let's say that we generate a sample of size 84 from the Loeb-Wally Pine data with replacement, just like we did on the previous slide, that some of the observations will be selected more than once, some won't be selected at all. Each of these samples with replacement will take the mean, and as I noted earlier, since we're sampling with replacement, the mean will be slightly different for each one of these samples. So, and then we'll repeat this process 1,000 times. And we do this hoping that the distribution of the data sets generated by this procedure, which is conventionally denoted by x bar star, again the bar got lost, will have the same sampling distribution as x bar itself. So just to kind of illustrate how this works, first of all, I just printed out the Loeb-Wally Pine data. I sorted it from smallest to largest so that we can see what's going on here. I believe the height is in meters, so the first tree has a height of 3.46 meters, second has a height of 3.77 meters, etc., etc. So then I try sampling from the set of heights of Loeb-Wally Pine trees with replacement. Again, I sort it from smallest to largest to give a better illustration of what's going on. You can see like 3.46 is in the data twice. That got sampled twice in this particular sample with replacement. 3.77 didn't get sampled at all. 3.88 got sampled once. 3.91, 3.93 didn't make it in the data at all. 4.12 got sampled twice. You get the idea. So when you resample from the data with replacement, some of the observations end up in the data several times. Some of them don't make it into the data set. And I only showed one example of sampling with replacement. But in principle, I could do this a large number of times. I'll show you in the next slide how you do this 1,000 times. But without printing out the data each time I sample with replacement a couple different times and take the mean of each sample with replacement, you see I get a slightly different mean for each sample like this that I generate. I get 32.285, 33.13, 38.477, etc., etc. So, in principle, I could do this a large number of times and get a big long list of sample means. This is making sense thus far. I'm hoping not to lose people immediately.
So
You know,
how are you telling the sampler, how many times is it supposed to try numbers from height or?
oh, that'll be the next slide. This is just to illustrate what we're doing here, that we're resampling from our data with replacement. Each resample with replacement, we're taking the mean. And I guess I can just go to the next slide to show how you would do this a bunch of times in R. The simplest way to repeat this process a large number of times in R is to use a for loop. If you've used any other types of programming languages or statistical software, you may have seen for loops before. If not, then hopefully this makes some sense. But in general, in any type of programming language, a for loop just tells your language to repeat a certain command a large number of times. So what this code says in R is, first of all, I create a vector of length 1,000. I just say repeat missing value 1,000 times. So I have a blank vector of length 1,000. Then I say repeat the following command 1,000 times and make the ith element of this blank vector equal to the mean of sampling from this data with replacement. So, in other words, I sample from the low-Lolly Pine data with replacement 1,000 different times. Each time I calculate the mean, I end up with this vector that I call x bar star. Of length 1,000, each one of the 1,000 elements is the mean of one of these samples with replacement. So far, so good still? Okay. So, in general, in R, if you use the syntax for I and 1:n, and as an aside, this is probably going to be about the hairiest R stuff that we ever do in this class. And once again, that for the homework on this stuff, you'll basically just be copying the examples I do in class with a couple minor modifications. But a for loop in R and most other languages, it says if you say for I and 1:n, that says R should repeat a command n times. The first time you repeat the command I is equal to 1, second time you do the command I is equal to 2, third time I is equal to 3, etc., etc. So on the previous slide, you'll notice x bar dot star of I. What that's saying is the first time through the loop, let the first element of x bar star be assigned to the sample mean. The second time through the loop, the second element gets assigned the sample mean. So basically, each element of this vector gets assigned to a different sample mean. So what was the point of what I just did? Well, if you'll recall from a few weeks back, the low-Lolly Pine dataset has a mean of 32.4 and a standard deviation of about 20.7. So the central limit theorem tells us that the sample mean x bar should have a normal distribution with mean 32.4 and standard deviation 20.7 divided by the square root of 84, which is about 2.26. I mean, strictly speaking, it's actually a t-distribution rather than a normal distribution. I mean, a t-distribution with 83 degrees of freedom is virtually identical to a normal distribution, so whatever. So in this case, we know the sampling distribution of X bar. Now let's look at the sampling distribution of X bar star, which is those 1,000 means that I generated from resampling the data. So if we just take the mean of the original data and the standard deviation divided by the square root of the sample size, we get a mean of about 32.4, standard deviation of 2.26 I just saw. So if I look at X bar star, this long vector of resampled means, and take the mean of all these resampled means, I get 32.45, virtually identical to the mean of the original data set. Oh, that's kind of cool, but what's really interesting is if you take the standard deviation of these X bar stars, we get 2.21, virtually identical to the standard deviation of the sample mean based on a sample of size 84, which seems too good to be coincidental, and it turns out it's not coincidental. In fact, we don't just have to look at means and standard deviations, let's look at the quantiles of X bar that we can estimate using the normal distribution, and also the quantiles of X bar star, which we can just get from the data itself. So what's the 25% quantile of a normal distribution with mean 34, whatever it is, standard deviation 2.26? Well, it should be about 30.84. And if we take the 25% quantile of this vector X bar star, it's 30.9. Whoa, almost exactly the same once again. Let's look at the 75% quantile. Theory tells us it's 33.89. If we look at X bar star, it's 33.88. Almost hit it right on the head that time. Look at the 97.5% quantile. Central limit theorem says that it should be 36.79 approximately. The 97.5% quantile of X bar star turns out to be 36.58. This is kind of weird that if the central limit theorem tells us that the sample mean should have a normal distribution with a given mean and a given standard deviation, and this vector X bar star that we just created not only has the same mean, the same standard deviation as this normal distribution, it also has almost exactly the same quantiles as this normal distribution. And if you recall, we discussed how can you tell if a data set's normally distributed. You can do these normal QQ plots, and lo and behold, it looks like this X bar star is almost exactly normally distributed. It may have some slight variance in the upper right tail, but I mean, in general, if your QQ plot looks like this, it means your data is normally distributed. So we see X bar star has the same mean, same standard deviation, same quantile, same shape as the sampling distribution of X bar, which we know is normal. In other words, the distribution of X bar star is exactly the same as the sampling distribution of X bar. In other words, if we had no central limit theorem, none of this theory to estimate the sampling distribution of the sample mean, we could just resample from the data and replacement like I just did and get a very good approximation for a sampling distribution without using the central limit theorem. In fact, if you take some upper-level statistics classes, you can show theoretically that under mild conditions, using bootstrapping as I just described, you will get the sampling distribution of whatever statistic you're interested in. And so what do you do once you have this sampling distribution? Well, in previous lectures, I showed how if you know the sampling distribution of X bar, which is normal, you can use that to calculate confidence intervals for X bar and do hypothesis tests and so forth. So this implies that we could also calculate confidence intervals and p-values to make hypotheses about the sample mean using x bar star rather than using the central limit theorem. So, in the past, when we've computed 95% confidence intervals for the mean, if you wanted to compute a 95% confidence interval for x bar, you can take the 2.5% and 97.5% quantiles of a normal distribution with mean 32.4 and standard deviation 2.26. But since we've just illustrated that the distribution of x bar star is the same as the sampling distribution of the original data, if we wanted to find a 95% confidence interval for the mean, rather than using the normal distribution and using p norm or q norm or qt or whatever function, we can just calculate this x bar star and then use the quantiles of x bar star. So, once again, if in the low-Wally Pine data, I illustrated in the past that if you want to find a 95% confidence interval for the mean, you can just take the 2.5% and 97.5% quantiles of a normal distribution with the appropriate mean and standard deviation. We end up with a confidence interval of about 27.94 to about 36.79. Well, if we didn't want to use the normal distribution, we could just look at the quantiles of this x bar dot star vector that I calculated, and the confidence intervals go from 28.26 to 36.58. And we end up with almost exactly the same 95% confidence interval without using the normal distribution at all. And we can also do hypothesis testing using the distribution of this data that under the central limit theorem, if we want to test the null hypothesis, the true means equal to 30, we can compute the probability of observing a sample mean as extreme or more extreme than what we observed under the assumption the null hypothesis is true. How can you do this using x bar star? Well, recall that there's a relationship between confidence intervals and hypothesis testing that you can say that the p-value corresponding to a given confidence interval is the alpha such that a confidence interval with coverage probability 1 minus alpha has the value of the parameter hypothesized under H0 on one of the endpoints of the interval. I know that is a fairly dense and convoluted slide, and I'm not sure if there's a simpler explanation for that, and it's not sufficiently important that I want to spend the next 10 minutes explaining it, but if you want to draw a picture or something to convince yourself of that, you can go ahead, or you can just take my word for it. But basically, the implication is that if you have a confidence interval for some parameter, or if you create a 1 minus alpha confidence interval for the mean such that the hypothesis value 30 in this case represents one of the endpoints of that confidence interval, then the p-value for testing the null hypothesis that the mean is equal to 30 is just equal to alpha, whatever the coverage level of this confidence interval that has one endpoint on 30. So, if you want to find the p-value for testing the null hypothesis, the mean equals 30, you find a confidence interval for the mean using x bar star with an endpoint at 30, and find the coverage of that confidence interval, then the p-value for testing the null hypothesis, the mean is equal to 30, is just 1 minus the coverage level of that confidence interval. So, in general, if you compute a one-sided confidence interval that ends at the alpha quantile of the data, that'll have coverage probability 1 minus alpha. So the implication is if you want to find the p-value for testing the null hypothesis, the true mean is 30, you can answer the question 30 is what quantile of x bar star. So you can just count the number of data points in x bar star that are less than 30 and divide by the length of x bar star. If you didn't follow all of what I just said in the last couple slides, don't worry about it. I know this hypothesis testing based on bootstrapping is highly confusing. I'm going to devote an entire lecture to this in a couple days. This is just a proof of concept mainly at this point, where I'm force-feeding you a lot of material in 3 slides. Oh, if to compute a confidence interval for the null hypothesis that the mean's equal to 30 using the central limit theorem, as we discussed before, we can find the probability of observing a value of 30 or less under a normal distribution with the known mean and standard deviation, then multiply that by 2 if we're doing a 2-sided test. Well, we can also test this null hypothesis using our Bootstrap data. We count the number of resampled means that have a mean of less than 30, divide by the total number of Bootstrap samples, 1,000 in this case, multiply it by 2 for a 2-sided test, and we end up with a p-value that's virtually identical to the p-value that we got from the normal distribution. So in addition to calculating confidence intervals using bootstrapping, we can also perform hypothesis testing. And a couple R commands I'm not sure I'd covered previously. If you say sum vector x, that just gives you the sum of all the elements of x. If you said sum 1, 2, 3, 4, that will give you 1 plus 2 plus 3 plus 4. In other words, a sum of 10. If you say sum x less than y, that will give you the count of the number of elements in x that are less than y. So in the previous slide where I said sum x bar dot star less than 30, that gave me the count of the number of elements of x bar dot star that were less than 30. And then I divide that by 1,000 to get the proportion of these resampled means that are less than 30. So this is kind of interesting, but up till now you may be sitting here thinking, okay, what's the point? So using bootstrapping, we can calculate confidence intervals for the mean, we can do hypothesis testing. That's nice, but we already know how to do it using the central limit theorem. Why are you torturing us with this weird, confusing bootstrapping thing when we can just do it using normal theory and it's a lot easier? Well, there's a couple reasons that you might want to use bootstrapping. First of all, bootstrapping works regardless of your sample size and regardless of how bad your data is. That if your sample size is small, you have major outliers, as I've said before, then the central limit theorem may not kick in, the confidence intervals that you calculate may not be valid. Bootstrapping, it works just fine, even if your sample size, even if you have a sample of size 3, for instance, one of which is a huge outlier. If you're ever worried about whether or not your sample size is large enough to use a t-test, you can use bootstrapping to check to make sure that you're getting the right answer. In fact, I'll give you a little tip right now that there will be a homework problem with a relatively small data set that has a bad outlier in it, where you're supposed to see the normal if you use a standard t-test, you'll get wrong confidence intervals, but if you use bootstrapping, you'll get confidence intervals are valid. So probably won't assign that homework for a while, but store that information away at the back of your brain. You may save yourself a couple points. But the main reason that bootstrapping is important is because it works just fine even if the sampling distribution of the statistic that you're interested in is unknown. For example, Let's say that you wanted to find a 95% confidence interval for the median, which might be a perfectly reasonable thing to do. As I've discussed in previous lectures, there's reasons to prefer the median to the mean in that it's resistant to outliers, resistant to skewness and stuff like that. If you have data with large outliers and or skewness, the median may be a more informative measure than the mean. Well, but if you read virtually every scientific paper that's ever been written in the history of science, they always report means rather than medians. Is that because the mean's better? No. It's because journals want you to report 95% confidence intervals for your statistics, and it's very easy to report a 95% confidence interval for the mean. You use the t-distribution. Anybody who's taken elementary statistics knows how to do that. But how do you compute a 95% confidence interval for the median? Well, beats me. Nobody knows how to do it, so nobody reports medians in papers, and a statistic that's potentially useful gets underutilized. So today I'm going to teach you how to calculate 95% confidence intervals for medians, and once you know how to do this, you will know how to do something that probably 80 to 90% of biostatistics grad students here at UNC and many of our faculty don't know how to do. So I'm trying to make it feel like this torture is worth something if you get excited about things like this. I know I'm probably the only one who's that big of a dork, but anyway. So let's say that we want to find a 95% confidence interval for the median. We can do exactly the same thing that we did for the mean. Create this median dot star vector of length 1000, use a for loop, resample from the data 1,000 different times, calculate the median of each of these bootstrap samples. We end up with this median dot star vector of length 1000. Each element of that vector is the median that you get after resampling from the data, one of the 1,000 times. So let's plot the histogram of this median dot star vector. It looks like that. What distribution is this?
Sorry, what was the NA in the past slide supposed to do?
Oh, in R, NA is just a missing value. So I initialize the vector to be length 1,000 with nothing but missing values, then I fill in those missing values. Whenever you initialize something in R, it's a good practice to set it to be missing at the beginning, so if you forget to fill in something, you can see that you forgot to fill it in. So at any rate, so I have these 1,000 bootstrap medians, and I can plot a histogram, and it looks like this. It's this weird bimodal thing. Bimodal means it has two peaks, basically. I don't know what distribution this is. It sure as heck is not normal. You certainly cannot use a central limit theorem or something like that to calculate a 95% confidence interval for this median, because it's this strange thing. But if you want a 95% confidence interval for the median, you can use bootstrapping, and it's easy. 2.5% quantile of median dot stars, about 26.62. 97.5% quantile is 41.13. Voila, now we have a 95% confidence interval for the median. If you're writing a paper someday, you want to report the median of some statistic and want a 95% confidence interval, that's how you do it. You can do this with medians, modes, ranges, interquartile range, odds ratio, whatever crazy statistic you can possibly think of, you can compute 95% confidence intervals using bootstrapping. This is precisely why I decided that this is worth teaching in an introductory class, just because, I mean, until the past decade or so, doing this sort of thing would be completely impossible. Now you can do it in R in a couple minutes if you know what you're doing. So I feel like this is a really powerful method that people should know about, even if it is a bit confusing. And I mean, like I said, the examples I'll ask you to do in this class will be fairly basic. I just want you to be aware that these methods exist. So if you're ever writing a paper and you want to report a confidence interval for a median or some other statistic like that, you can just brush off your old 610 notes or talk to your favorite statistician, not just say, well, we can't report the median because there's no way to compute a confidence interval. Actually, there is a way. Likewise, we can do hypothesis testing. Say we want to test the null hypothesis that the median is equal to 30. We can use the same logic I did for hypothesis tests about the mean, calculate the number of medians that are less than 30, multiply by a two-sided test, divide by 1,000, we get p-value of 0.816. We fail to reject the null hypothesis that the median is 30. So, as I said before, in almost all published manuscripts, people report means and p-values and confidence intervals for the mean. This isn't because it's the best summary statistic. In fact, it's misleading in a lot of cases. The only reason people like the mean so much is because we have the central limit theorem. And since we couldn't compute the exact sampling distribution of the median, there didn't used to be a way to compute confidence intervals and p-values. As I just said, it looks like I got ahead of myself on these slides. And so, using bootstrapping, you can approximate the sampling distribution for any statistic of interest whatsoever, and hence compute p-values and confidence intervals for any statistic. Well, there are a couple of cases where bootstrapping won't work, but that's way beyond the scope of this class. In the next couple lectures, I'll give you some more examples of where bootstrapping is useful. Another reason why you might want to use bootstrapping is, even if you're making inferences about the mean, if you're worried that the central limit theorem doesn't apply, if your data set's small, if it's skewed with bad outliers, the usual cases where the central limit theorem can blow up, use bootstrapping and you won't have a problem. And bootstrapping still has some limitations. It requires that you have a random representative sample of the population of interest. I know I say that over and over again. But if you have a biased sample, there's no sort of statistical method that can help you. You're just sunk from day one. And bootstrapping, at least the way that I've described today, still requires that your samples are independent. If your data is correlated, you can't use bootstrapping to get valid confidence intervals. Well, as I say here, that isn't quite true. There are bootstrapping methods that people have developed for dealing with correlated data, but that's way beyond what I would ever ask you to do in this class. To be honest, I would have to look this up myself. I couldn't tell you how to do it off the top of my head. I just know the methods are out there. Oh, things to remember for today, that if you sample from a given data set with replacement, you can approximate the sampling distribution of any statistic of interest for that data set. Whether that statistic is median, standard deviation, interquartile range, whatever the case, whatever the statistic of interest may be. And if you have a bootstrap approximation of the sampling distribution, you can compute confidence intervals and p-values for medians, interquartile ranges, anything that you're interested in. And this means that we can compute confidence intervals and perform hypothesis tests even when we don't know the sampling distribution, which the vast majority of cases we won't, except in the case of the mean typically. And new R commands today, a for loop tells R to repeat a certain command a specified number of times, and you can also use the sum command to sum up a vector or count the number of times that a vector is less than a number, or something like that. Any questions about any of this? Anybody's head ready to explode? Okay, I don't see steam coming out of anybody's ears. That's a good sign. I apologize, it's a little bit confusing, as I said, but as I also said, this is very powerful stuff that I feel like people should know nowadays, and I'll try not to make the homework too horrific on this.